Welcome to this problem solving session. I'm Shreya, one of the TAs of this course on Essentials of Data Science with R Software. So, today I'll discuss some concepts which will be helpful in framing your critical region for testing of hypothesis. But before I move into that, I would want to know if you have any particular doubt from any of the lectures, problem solving sessions, or any concept that you would want to brush up on. Please let me know. All right. So I don't think anybody else has joined yet. So just in case you want to say something, please unmute yourself and start speaking. All right. Okay. So last class we learned how to conduct tests of hypothesis. So what did we do? We essentially there was some what do I say? Some null hypothesis that we had in our mind, some alternate hypothesis that we had in our mind, and then we defined some test rule based on some test statistic, and then that would follow some distribution, and then we would define cutoffs and then formulate the rule. All right. This was the overarching, what do I say, pathway or trajectory of of conducting a test of hypothesis. Now, there was a question, or rather, I wanted to clarify that if you have a hypothesis like this versus h1 mu greater than 0, it doesn't necessarily mean that your test statistic should be greater than some k. So this doesn't imply if here we have greater than, here also we'll have a greater than sign. Okay, so in order to understand this scenario, I would like to demonstrate how actually we derive this critical region. We were talking about some critical region. Okay, let's say this is W and this is W complement, and we have our sample. So if this n-dimensional point is lying within this space, then only we are going to reject H naught. Now, how do I make this space? That is the key question. Okay. And while describing this, I said that if you have h1 mu greater than 0, then it is not necessary that your test statistic should also be greater than some k. Okay. But I also said that the current examples that you have learned, testing of mean, testing of variances using normal distribution, there this relation is being followed, but that doesn't mean that it will be followed everywhere else. All right. So in order to demonstrate this, I'm going to show you how we are arriving at this uh, critical region definition. All right. Okay. So first, yeah, do you want to say something? Okay, okay, fine. So in order to define the critical region, we use the Neyman-Pearson lemma. So Neyman-Pearson lemma, it says that let's say your H naught is your theta is equal to some theta naught and your H1 is theta not equal to theta naught. All right, some other hypothesis. Now this, uh, if you are to reject null in favor of your alternate hypothesis, what is your natural inclination? Your natural inclination would be that given my data, likelihood of theta equal to theta naught should be less than likelihood of theta equal to theta not equal to theta 1. Okay, so this is by natural intuition, we would want that this likelihood should be less than the likelihood of getting what we have gotten if theta is not equal to theta naught. If the null likelihood is less, then only we can say that okay, our evidence is favoring towards the alternate hypothesis, right? Is this clear? Okay. So then by Neyman-Pearson lemma, what do we say? If we have to say that likelihood of theta equal to, or likelihood of, I should write here, theta naught given my data that we have already observed by likelihood of theta, let's say I write it like this, theta equal to theta 1, which is not equal to theta naught. Alright. So likelihood of theta 1 given x1, x2, xn. This should be less than equal to some k. Okay. And then from here, we are going to formulate whether the test statistic that we have in our hand should be greater than, equal to, or less than this k. Okay. So we are going to derive from here to here. So let me take an example of a normal distribution. All right. So let's say here I have x1, x2, xn. This follows some normal mu1. Okay. For the timing, I'm keeping it to be 1. Okay. So if all of these follow normal mu1 and I'm going to test mu equal to 5 versus I'm going to test three hypotheses. H1 will be mu greater than 5, H2 will be mu not equal to 5, and H3 will be mu less than 5. Alright, so by Neyman-Pearson lemma, what do we get? Likelihood of mu equal to 5 given x1 to xn by likelihood of mu equal to, let's say, mu1 given x1 to xn. This should be less than or equal to k. Okay. Now, likelihood is essentially what? Since x1 and xn are independent, they are IID. So this is exactly like the joint PDF. Okay. So we are going to write the joint PDF of x1 to xn. Alright, f x1, comma x2, comma xn. So how will we write this? This one, let's say we'll write it as, so if x follows normal mu 1, then fx will look like 1 by root 2 pi. Sigma here it should come, so it is 1 e to the power minus half into x minus mu square. Okay, so if we have n random variables which are independent, this is going to replicate n times, okay, where x will become xi. So what do we have? We'll have 1 by root 2 pi. Sigma is there, so this to the power n e to the power minus half into summation I equal to 1 to n xi minus mu whole square. Okay, so this mu will be mu naught. Okay, and this one will be 1 by root 2 pi to the power n e to the power minus half summation I equal to 1 to n xi minus mu1 whole square, and this is less than equal to some k. So this cancels out. So we'll have e to the power minus half summation xi minus mu naught whole square minus summation xi minus mu1 whole square. This should be less than equal to k. Alright. So now if we just take a logarithm, then we'll have minus half summation xi minus mu naught whole square minus summation xi minus mu whole square should be less than or equal to k. Alright, now let us just expand this. So here we have minus half summation xi minus mu naught whole square minus summation xi minus mu1 whole square. This should be less than or equal to k. So let us just expand what we have in the second bracket. Minus half summation xi square minus 2 mu naught summation xi plus n mu naught square minus summation xi square minus n mu1 square, and then what do we have? Plus 2 mu1 summation xi. Alright, this should be less than or equal to k. So this and this cancels, and if we take summation xi as common, then we have 2 summation xi. Let us take it to be. So here we have mu1 minus mu naught, and then also sum plus n if I take common mu naught square minus mu1 square. This is less than or equal to k. Okay. So if this goes, so this part is this should be minus something. So if it goes on the right side, it will be less than k. So we can write this as minus, this 2 cancels, let's say. So summation xi mu1 minus mu naught should be less than or equal to some k star. Is it okay? Now, just look at the three hypotheses. Okay, so this is this hypothesis is actually mu1 greater than mu naught. This is mu1 not equal to mu naught, and this is mu1 is less than mu naught. Alright, so here let's say this is your final whatever you've gotten. Okay, so if we take minus on that side, your hypothesis is summation xi mu 1 minus mu naught should be greater than or equal to some k double star. Is it okay? Now, if your hypothesis is mu1 greater than mu naught, then this remains positive. Then this reduces to, if this is mu1 greater than mu naught, this reduces to summation xi greater than c. Alright. If you have H3, mu1 less than mu naught, then this quantity will be negative. So summation xi, if you take as your statistic, the sign will be reversed. You would have summation xi less than c. Okay, and H2 is mu1 not equal to mu naught. It could be either of the situations. Either this, that would imply either summation xi is greater than some c, or summation xi is less than some c prime. Okay, either or and or. Okay, so see, for H1 you have mu1 greater than mu naught, and your test statistic, this should be some form of this summation xi. This is also greater than some c. Now once you have, this is your critical region. Okay, this will guide your critical region. Now how do we proceed? So summation xi is actually n x bar, or if we divide this by n, then we'll have x bar, which will follow your normal mu 1 by n, and then from here x bar minus mu by 1 by root n, this will follow normal 0 1, and then we can devise cutoffs like this, that, and then if this thing summation xi is greater than C, then this quantity will also be greater than C. So that's how we define a right tail test. That if it is too extreme, if it is falling in this region where the area, let's say it falls in this region, I'll draw it with a different color. This is your T observed, okay? So T observed is falling in this region such that anything greater than a probability that this distribution of the T statistic is greater than wherever your T observed falls, that is this area on the right, this is less than 0.05. This is by p-value definition. And by cutoff definition, we see that it is falling beyond the, let's say this is your 1.64, normal 0, 1, uh, upper alpha point where alpha is 0.05. All right. So this is how we devise our critical region. Similarly, from this one, summation xi less, if it is less than C, then this quantity under H naught, this will also be less than some C prime. Okay. This would imply that T is less than some C prime. Now, what is the distribution of T? T also follows a normal 0, 1. So if you have something T less than C prime and you have to find, then if this is your normal distribution, area below this, let's say 0.05, then if your T falls in this region, T observed, then you are going to reject H naught. Okay. If T falls in this region beyond minus 1.64, okay, then you are going to reject, and your P value will be probability this area. All right. So that area will be less than 0.05. Is it clear? Now, in case of a two-tailed test, what happens? Let's say when you are considering H2, mu1 not equal to mu naught, then you have to devise your test in such a way that you are excluding if it falls in both the extremes. All right. You are going to exclude if it falls here, or you are going to exclude if it falls here. And how are you devising it? This is a symmetric distribution. So whatever, if this is minus 1.64, this will be 1 plus 1.64. Sorry, this will be. So you have to devise it in such a way that your total alpha is 0.05. So you have to distribute this area between the two extremes. All right. So area above will be, so this area shaded in green, this will be 0.025, and this area will also be 0.025. All right. So if your test statistic is falling in this region here or here, then you are going to reject your null hypothesis. So since this is the normal 0, 1, this point will be 1.96 and this is minus 1.96. Please note, if in case you are, hopefully you'll be given all cutoff values during your exam. But if not, it would be good if you can remember these cutoffs. Okay. So if yes, that will depend on your hypothesis. So this both tail hypothesis is actually mod T greater than T observed. This will give you a p-value in this case. In this case, your p-value will be T less than T observed. Okay. And in this case, it will be probability T greater than T observed. All right. This will give you this green shaded area here. This will give you actually the purple shaded area. All right. And if you do this, probability t greater than t observed, what you are doing is you are considering anything that falls to the right of this blue, because your t observed could, you are doing more t greater than t observed, which means probability t greater than t observed plus probability t less than minus t observed. So if this is your t observed, t greater than t observed is this blue area, and t less than minus t observed, because this is symmetric, this is this shaded lower blue area. And together this area should not exclude 0.05. That is, your p-value will always remain less than 0.05, and thus you can reject your null hypothesis in favor of the corresponding alternate hypothesis. So this is what happens in case of a normal distribution. All right. But this is not always true. Again, I'm saying it is true for all the distributions that you have learned so far, or the tests for equality of means, tests for equality of variances for a normal scenario. But if the distribution changes, this correspondence, that if this is greater, then my t should also be greater. If this is less, the t should also be less. That will break if that might break if the underlying distribution is not normal. Okay, so I'll give an example just to demonstrate this. So I think you have learnt about exponential distribution, right? Okay, so let us consider that x1, x2, xn, this follows an exponential with mean theta. Okay, so if mean is theta, then the parameterization is that if xi is 1 by theta e to the power minus x by theta, if x greater than equal to 0, 0 otherwise, and your theta is always greater than 0. Alright, if this is your parameterization, then how do you devise a critical region? Let us assume you have h naught is theta equal to 2 and h1 similarly theta greater than 2, theta less than 2, and theta not equal to 2. Okay, now we'll follow the same procedure and try to devise my decision rule. Alright, so by Neyman-Pearson lemma, what is the intuition? If I have to reject my null in favor of the alternate, then likelihood of getting the likelihood of the null hypothesis should be less than likelihood of the data, likelihood of the alternate parameter given our data. Okay, so L theta naught given x1 to xn by L theta 1, I'm writing for the time being, x1 to xn, this should be less than or equal to k. Okay, this theta naught, I'll write it like this. This is theta naught equal to 2, and this we'll have theta equal to theta 1, which is greater than 2. This is theta equal to theta 1, which is not equal to 2. And here we'll write theta equal to theta 1, which is strictly less than 2. Okay, less than or equal to greater than whatever combination it may be. Alright, so by Neyman-Pearson lemma, we have this. Now, likelihood is nothing but joint PDF. So we are going to write the joint PDF. Here I have written the formula for 1, and these are IID. So what it will be? It will be 1 by theta e to the power minus xi by theta. This product I equal to 1 to n. Numerator will be theta naught and denominator will be I equal to 1 to n 1 by theta 1 e to the power minus xi by theta 1, that should be less than or equal to some k. Okay, so we can write this as 1 by theta naught whole to the power n e to the power minus 1 by theta naught summation xi by 1 by theta 1 whole to the power n e to the power minus 1 by theta 1 summation xi less than equal to k. Okay, so we can write this as, this one will be theta 1 by theta naught to the power n e to the power minus 1 by theta naught summation xi plus 1 by theta 1 summation xi. This is less than or equal to k. Alright. So that we can, if we move this to the right hand side, we'll have e to the power minus 1 by theta naught summation xi plus 1 by theta 1 summation xi should be less than or equal to some k star. Okay, because it will be multiplied with this factor. Okay, this is not negative, so there is no question of change of uh, this inequality sign. Okay, theta 1 is also positive, theta naught is also positive. Alright, now this one, if we take logarithm, then we'll have 1 by minus 1 by theta naught summation xi plus 1 by theta 1 summation xi. This is less than or equal to some k double star. Alright, so if we take summation xi common, this would be, any questions? Okay, I'll come to your question later, Janvi. Let me first complete this. So here we have theta 1 minus theta naught. This is less than or equal to k double star. Alright, now from here I want you to focus on the hypothesis that we had looked at. First one was theta, the alternate hypothesis were theta equal to theta 1, which is greater than theta naught. A2 was theta equal to theta 1 not equal to theta naught, and A3 was theta equal to theta 1, which is less than theta naught. Now let's say if HA1 is true, then theta 1 minus theta naught will be a positive quantity. So then this ratio will be a positive quantity. Then your rejection rule remains summation xi less than sum c. Okay? And here on the other end, if A3 holds true, then theta 1 will be less than theta naught. As a result, this quantity will be negative, and thus the inequality is going to change. It will become summation xi is greater than c. So you see here, the alternate was that theta is greater than some theta naught, but our rejection region will be based on summation xi is less than c. And here the alternate was theta is less than theta naught, but our rejection rule is going, the sign is going to change. Okay, but the same thing would not have occurred if this parameterization, the mean is, let's say, 1 by theta. Okay, then we would have had theta e to the power minus theta x and 0 otherwise, and everything would have proceeded like this. Situation would not have, I mean, this reversal of inequality would not have occurred. So that is why I'm saying, even though for the test that you have learned, you know what happens if it is in each of these scenarios, don't make it as a ground rule and don't assume that it will follow everywhere else. Okay, so this is one such example where your decision rule criteria might be reversed based on your alternate hypothesis. Okay, now you have not learnt about this uh, distribution of summation xi in case of exponential variable. This will go to some gamma distribution, and then that is also some positively skewed distribution, and then we are going to define cutoffs similar to this. So, okay, let me just complete this and I'll revisit. Okay, I explained 1 second, but I'll recapitulate once more. But let me just finish this. Okay, all right. So here you see that this one was theta equal to theta 1 greater than theta naught. Corresponding rejection is summation xi less than c. So if this one will follow some gamma distribution. So for the time being, just focus on this thing. Summation, this is theta 1 greater than theta naught, and this is summation xi will be greater than c if theta 1 is less than theta naught. These are the two cases that we are considering. So let's say your t will also be some t less than c, the final test statistic under h naught, and this will also be t greater than some c prime or something. Okay. So here what will you do? Here you have a positively skewed distribution. Okay, this is a positively skewed distribution. So if theta 1 is greater than theta naught, then your p-value should be, this area is your 0.05. So this will be given from the tables. Okay, so you have to find out this one, the area below which 5% area lies, the point below which 5% of the total area lies. All right. So then you have to check if your t statistic that is falling in this region, okay, and the area below it is the p-value. So this actual shaded area is your p-value. So p will be t less than t observed. Okay, and your point t observed should be less than your critical point. So this will be some, what do I say, some gamma something. Okay, and this one here, if you have t greater than t star, then you have to find this point. Let's say this point is such that the area above it is 0.05, and if your t observed is lying over here, let's say t observed falls here on the x-axis, then this shaded area beyond t will give you the p-value. So p will be t greater than t observed, and your t observed should be greater than this cutoff point. Okay, some gamma cutoff, alpha, upper alpha gamma cutoff. Okay, now note, since this is not a symmetric distribution, this point and this point, okay, so let's say this is, I call it 1 minus alpha. So upper alpha point is any distribution. If you take this, if I say is the upper alpha point, that means area below above this point is alpha. Okay, so for a skewed distribution, this point will be gamma 1 minus alpha, and this point will be gamma alpha. Okay, so note, if you do not have a symmetric distribution like normal or T, then you would have a skewed distribution. And in that case, this lower alpha point or upper 1 minus alpha point and your upper alpha point, they will not be, what do I say? They are not symmetric about 0. So if this is, let's say, plus 2.3, this will be minus 2.3, that will not hold. Okay, if this can be 2.3, this can very well be minus 3.5, or it can very well be 0.02. Is it clear? So this is how you devise your test statistic from the Neyman-Pearson lemma. What is the Neyman-Pearson lemma stating? It is stating that the likelihood of getting your data x1 to xn when the true value of theta is theta naught by the likelihood of getting whatever you've observed when the true value is theta 1, that ratio is less than or equal to some k. The natural intuition is this: you have your null hypothesis, that is a no change sort of a situation. You have your alternate hypothesis, that is your usual suspicion. Okay, let's say I'm testing a bulb. I have been told that this bulb functions for 3 months. But over time, I'm seeing I have, let's say, 100 bulbs. I am seeing most of them are becoming dysfunctional around 1.5 months. So if I want to go ahead with the testing of hypothesis, my usual intention will be, if theta is the average time or lifetime of any randomly sampled bulb, if H naught is 3 months, my suspect is maybe it is not 3 months, it is 2 months. So maybe H1 is less than two or less than three. Okay. So then if I have to prove my suspicion, then I have to show that the likelihood of the average duration or lifetime to be 3 months is actually less than the likelihood of the, what do I say? Is that it should be less than the likelihood of obtaining the likelihood of the average lifetime to be 2 months, because we are rejecting, always remember, we are rejecting null in favor of the alternate hypothesis. Okay, it is not that the alternate hypothesis is the ground truth or the null hypothesis is the ground truth. We are just trying to gather evidence so as to prove that maybe we should or we want to believe our alternate hypothesis. And that is how we are intuitively designing this likelihood criteria. And then by mathematical derivation and calculations, we are landing up at defining the critical region. Okay, so Neyman-Pearson lemma that states that if I am doing this ratio, if I'm calculating this ratio, then the test rule that I am going to get, that is the most powerful test among all tests. Okay? Yes, that is what we want to believe. Okay. Likelihood likelihood is actually product of the probability. So if you have likelihood theta given x1 to xn, mathematically you can write it as fx1 to xn given theta. So since this is your PDF or joint PDF. Okay. And since usually xi's are IID, you can write this as f of x1 into f of x2 into f of xn. Okay. Okay. Actually, uh, whenever you are defining a joint PDF, that time, so let's say you are sampling from a normal mu1 distribution. Okay. So if I tell you that sample from a normal mu1 distribution, take, I mean, actual samples, I have to tell you the value of mu, right? I have to tell you that sample from normal mu1, then only you will be able to do an R naught. R naught, and then you are taking the, let's say, 10 mu equal to 5. So whenever I'm drawing samples from a distribution, that time theta or the parameter is actually given. Likelihood mathematically is the same thing as joint probability, joint PDF, but likelihood concept is that you are trying to find out, uh, uh, I mean, likelihood states that the data is already provided to you. You are making an assumption on the nature of the data, and then you are finding out the probability of that population parameter to be some theta. Okay. Uh, did I make sense? Or do you still have theta is a population parameter. So let's say this is your population. All right. Let's say, let me give you an example. Let's say I want the height of Indian females. Okay. So I have some 1.4 billion Indians. If I calculate and tabulate all their heights and get the average height, that would be my theta true value. But this is not possible because of logistics reasons, cost, and so many other socio-economic reasons. So if I have to estimate the true value, what do I do? From the entire Indian population, I take a representative sample. Let's say from each of the states, based on their population proportion, I take I take that many number of proportional number of females, okay, from all parts of India, and then I get the average height. Let's say I collect 10,000 data, and then X bar, I'll have the sample average. Okay, so this actually, if I say that this is an estimate of the population parameter. So this 10,000 individuals, that will form my sample. Okay, and that will give me my X's, the data. And I'm going to use this data to estimate the true parameter. So theta is actually the population parameter. Okay, any other doubt? Okay, I just showed it, but I'll explain it briefly once again. You can go back, this recording will be available on YouTube. You can go back and check as to how we can derive it, okay? So, stepwise, if I have to tell you, were you there when I was explaining this problem? Okay, I'll repeat once again. for everyone who has joined late. So, Lehmann-Pearson lemma is clear to all, right? If not, you can please unmute yourself and tell me if you have any questions. So, this is a lemma which defines the criteria for getting the most powerful tests. Okay. Now, how do I use this criteria to test my hypothesis? For that, what let us just consider this normal example. Okay. So I have an IID sample from normal mu1. My null hypothesis is similar to that bulb example. Okay. So my null hypothesis is mu equal to 5. And alternate, let us consider three alternates. H1 mu greater than 5, H2 mu less than equal to 5, and H3 is mu less than mu not equal to 5, and H3 is mu less than 5. Okay. So what will I do? First, I'll write the Neyman-Pearson lemma in equation. So I am going to write likelihood mu equal to 5, that is under null, given x1 to xn, by likelihood mu equal to mu1, whatever is under alternate, x1 to xn less than equal to k. Okay. From there, I am going to, so likelihood is actually the joint probability. So I am going to write the joint probabilities under null and under alternate. That is what I have done. This one, this value is your likelihood or joint probability under H naught, and this denominator is your joint probability under the HA, alternate hypothesis. Okay. Then I have solved this one. Okay. If you have multiplication or division with a negative number, anything if you multiply or divide with a negative number, any inequality, then the sign changes. So we are being mindful of that, and then logarithm will not change our inequality sign. So that's why it is not changing. Then if you expand this, you would land up here. Okay, after expanding this uh, expression, you would land up at something like this: summation xi mu1 minus mu 0 less than equal to k star. Now, if you just, this is your rejection rule because it has come from the Neyman-Pearson lemma. Okay, one second. All right. So now you know this thing. Once you arrive over here, then we'll take a look at the null alternate hypothesis. So if mu1 is greater than mu naught, then okay, from the previous one, you see here we have a minus sign when we had less than equal to some constant. If we multiply with a minus sign this side also, then our sign is going to change. This will become a greater than or equal to. That is exactly what I have written over here. Okay. Now I'm going to look at my alternate hypothesis. This one says mu1 is greater than mu naught. Okay. So if that is true, this quantity in blue, this is actually a positive quantity. So this one, if I divide, if I move it to the RHS, then the criteria becomes summation xi greater than c. Alright? And then if H3 is my alternate hypothesis, then this quantity will be negative. So when I move it to the right hand side, I'll have summation xi less than c. Okay? So this is the rejection region. Now how do I devise C? Okay, in order to devise C, we have to use our type 1, type 2 error criteria. Alright, so what was our type 1 and type 2 error criteria? We saw that, let's say this is your ground truth, okay, and this is your prediction. Okay, you can have four, that H naught is true. This is H1 is true. This is your prediction H naught is true. Oh, this your prediction is actually reject H naught or do not reject H naught. It is not good to say accept H naught. It should be the correct terminology is we fail to reject H naught. But I have written accept for simplicity. Now, if H naught is true and we are accepting H naught, then we are making a correct decision. If H1 is true and we are rejecting H naught in favor of H1, then also we are making a correct decision. Alright? But if we are rejecting H naught when H naught is true, that is actually my type 1 error. And if we are not rejecting H naught given H1 is true, then also we are making some error, that is the type 2 error. Okay, now I explained it in the last class. It is not possible. If the golden scenario would have been if we could control both type 1 and type 2 errors simultaneously. But that is not possible. Okay, if we control one too much, another will be inflated. Okay, and also we have something called power, which is like 1 minus probability of type 2 error. Okay, so power of the test is that this is actually the power of the test. Something is wrong, something should be rejected, and it is rejected. So this is actually representative of the power of the test. Okay, that H naught, the null, my suspicion should be followed, and I'm following that suspicion. That is the power of my test. Alright. So, as I was saying, since we cannot control type 1 and type 2 errors simultaneously, what do we do? The way out has been proposed as this. Since type 1 error is the more grave situation, what do? We fix that probability type 1 error should be less than or equal to alpha. This is my level of significance. Okay. So we say, if I say 5% level of significance, then I'm specifically focusing that type 1 error rate, I'm not going to let it exceed 5%. Okay. And then first we fix this type 1 error rate, and then what do? Then we try to maximize our power. All right. So this is the way out, and this is what we follow. So once going back to the decision rule, so let's say this is my criteria now, summation xi is greater than c, then I have to know what my c is. Okay, so c point will be devised based on this probability of type 1 error less than or equal to alpha. So what do? Here I have to go probability summation xi greater than c should be less than or equal to 0.05. That is my alpha. Okay, so this one I make some changes. Let summation xi we know follows normal mu and 1 by n, right? Xi follows normal mu 1. So summation xi will follow, sorry, it will follow n, mu and n. Okay, so here if I write 1 by n summation xi, then it will follow normal mu 1 by n. Okay, so this one I can write as probability x bar is greater than some c prime. This has to be less than or equal to 0.05. Now x bar also is a normal mu 1 by root n. Okay, so if I just transpose it to x bar minus mu, so okay, not exactly mu but mu naught, because probability of type 1 error is what? Rejecting null given null is true. So what are we doing? This is my probability rejecting null, rejection region, given mu equal to 5 or mu equal to mu naught. This is my probability of type 1 error. This is summation xi less than c, given we are rejecting h naught, given h naught is true, given that mu equal to mu naught. Alright. So then x bar minus mu naught, if I just transform here, mu by, this will be 1 by n, sorry, 1 by root n, that follows a normal 0, 1 distribution. So if I write here x bar minus mu naught by 1 by root n, that will be greater than some c prime, and this probability should be less than or equal to 0.05. Now this one we know is a normal 0, 1 distribution. So here we have a normal 0, 1 distribution. We have to find C such that probability of this quantity exceeding C should be less than 0.05. So that is how we define this cutoff point. That is, let's say Z 0.05, which will be 1.64 in case of a normal 0, 1 distribution. So C is actually this point, because you see anything having greater than 0, C prime, if this probability greater than equal to C prime, that will not exceed 5%, because the area above this point is actually 5%. So do you understand how to do it? First things, we'll write the Neyman-Pearson lemma, we'll get the rejection rule, and then since we are capping type 1 error to our desired level of significance, we are going to compute this thing. Probability reject H naught given H naught is true. Restrict it to 0.05, then solve, we solve it, and so that it the test statistic under H naught, it follows some known distribution, and then based on whether we have greater than, less than, or whatever sign we have over here, based on that we try to find out this probability. Where should we devise our cutoff such that this probability less than equal to 0.05 holds true? Is it okay? Did you understand? Hello? Okay, so did you understand how we are using Neyman-Pearson to construct the test rule and then formulate the cutoffs and then carry out our test? Okay, so this is the flow, how we actually do it. So you can give it a shot, you can try out all the other tests that you have learned, and right from the Neyman-Pearson lemma, you'll be able to derive the test rules and then devise the cutoff points of the distribution as well. So if moving on to the next one, let's say in your exam, if you're given a question like this, that it follows some IID exponential mean theta, you have to formulate, let's say you are given this x1 to xn, it follows some exponential 1 by theta. You have, or rather the PDF is only given 1 by theta e to the power minus x by theta, x greater than equal to 0, 0 otherwise, and theta is greater than 0. Now if you are asked to find out, you are given values of x1 to xn, and you have said that at 5% level of significance, you test for the hypothesis H naught theta equal to 2 versus H1 theta equal to 3. What are you going to do? You are going to write likelihood of theta equal to 2 given x1 to xn, and then probability likelihood theta equal to 3 given x1 to xn, and then putting the values of 3 in the 2 and 3 in the joint PDF, you would have some formula, some ratio that is greater than C. It might come x bar greater than 3 by 2, something, something. So let us just solve this and then we'll see. Okay. So here theta equal to 2, if you do, then you will finally end up at this, okay, you'll end up at some sort of inequality, that 3 by 2 is greater than something, okay? Any form. So now, then if you're also told this, that the rejection rule is also specified, that if this happens, then I'm going to reject, and if this doesn't happen, then I'm going to accept. Is it all right? So this will be your joint PDF. So you will have to write 1 by 2 to the power n e to the power minus summation xi by 2 by 1 by 3 to the power n e to the power minus summation xi by 3 should be greater than equal to k. Okay, so if this you have to just simplify and get some 3 by 2 to the power n e to the power, let's say 1 by 2 minus 1 by 3. That would be summation xi by how much? 1 by 2 minus 1 by 3, or minus, this will be half minus 1 by 3. So it will be 6 minus 3 plus 2. So it will be minus 1 by 6. So this will be actually minus 1 by 6 is greater than equal to k. Alright. So then this one follows some other distribution, but that's what I'm saying. If you're asked to formulate, this is how you should formulate, and then you should see the type 1 and type 2 errors, and then specifically the type 1 error, restrict it to your level of significance, and then try to derive it. Okay. Is it okay how you should proceed if you are not confident about the ready distribution? For the exam purpose, hopefully you will get problems like this, testing of means of two normal distribution, testing of variances of two normal distributions, where you assume that the underlying distribution is normal. Okay, but this is just for your uh, clarity of concepts that I'm showing you this. Is it okay? Anything else? Please let me know. This session is meant to be interactive and is meant to clear your doubts with respect to all the problems, so that you are able to give your exams properly. So if you have any doubts, you can let me know. I think Janvi Prajapati you have written something, but the question is incomplete. Can you please unmute yourself and tell me what is it that you're having problem in? Okay. No, it's there. An ordinary deck of card 52 is randomly divided into 4 piles of 13 cards each. Compute the probability that each pile has one ace. Okay, I'll just copy yours. So, how would you approach this problem? Okay, so how did you do it? Not getting in the sense? Okay, Is this an assignment question? Okay. All right. Okay. Okay. Was it explained in the lecture? All right, understood. Okay. So here what they are saying, an ordinary deck of 52 cards is randomly divided into four piles of 13 cards each. Compute the probability that each pile has exactly one ace. Okay. So 52 divided into four piles. Okay. So if we divide this, let's say, into events. All right. You could have four situations. Let us divide. Where is it? Ah, let E1 be the event. Where is it? Can you see my marker? Okay, fine. So let us divide events. E1 is the event, let's say ace is in any of the four piles. Okay. E2 is the event that ace, let's say ace of spades. Okay. E2 is ace of spades and ace of hearts in different piles. Okay. You have four piles, one, two, three, and four. First, you say that ace of spades should come here. Then if spades comes here, heart has to go somewhere else. Alright? So heart and spades have to be in different piles. Okay? E3 is your event, let's say that ace of spades, ace of hearts, and diamond are in different. And E4 is that all in different. Okay? So then your probability you have to find a E4. Is it okay? Now, now we are going to get probability of E4 is what we need. Okay, so this is going to happen if E1 occurs and E2 occurs and E3 occurs and E4 occurs, right? Do you agree? So this one you can write it as probability E4 given E1 intersection E2 intersection E3 into probability of E1 intersection E2 intersection E3 by conditional probability. Is it okay? Then this thing, again you can break it down. Probability E4 given E1 intersection E2 intersection E3 into, again you break it down further, probability E3 given E1 intersection E2 into probability E1 intersection E2. Then you again break it down. Probability E4 given E1 intersection E2 intersection E3 into probability E3 given E1 intersection E2 into probability of E2 given E1 into probability of E1. Okay. Now probability of E1 is what? Ace of spade is in any of the four piles. Four piles. So this probability is actually 1. Probability of E1 is actually 1 because it is supposed to be in any of the four piles. Alright. Now probability of E2 given E1 is that, let's say I have fixed in, let's say it is in one of the, what do I say? It is in one of the piles. Okay. So then probability E2 given E1 means that the, how do I put it? Spades and hearts in different piles. So it means that in that particular, whatever pile we have put spades in, the remaining 12 of, uh, so we have removed one card. Okay, so 52 minus 1. So currently we have 51. All right, and from there 13 have been put in one pile, out of which one an is a spade. Okay, so 51 minus, sorry, 52 minus 13, the remaining 39 from, so out of these 51, whichever is left, so what I'm saying is I have already given one card. So I have 51 cards left, right? So E2 is what? E2 is ace of spades and ace of hearts in different piles. So that means that this, yes. So just help me frame the statement why it is 39 by 51. The remaining. Hmm. Yes. Yes, given that if we have already this one 1 plus 12 is already there, so we have 39 other choices to fill out of this 51. Okay, so E2 given E1 will be 39 by 51. Then the next one, E3 given E1 intersection E2, this will actually be, so from this 50, so 1 is also again gone. From here we have 50. So this will have 12 and 12 cards. So what is actually left? That left is 50 minus 24. That is 26 by 50. Okay. And then probability E4 given E1 intersection E2 intersection E3. This will be how much? This will be again 1, so 12. So from 49, we are going to get 49 minus 36. 49 minus 36, that is 13. And then if we plug in the values, we are going to get the required probability. Is it clear? Okay. Anything else? Assignment 9. Row by, 1 second, I'm not able to understand. 1 second. I'll stop my screen share. Where are you? Uh, yes, yes. Week 12. All right, I'll solve it. I'll solve it. Uh, uh, you check the question number. Meanwhile, I'll solve that question, assignment 9 question, and then we'll get back to your question. Is it fine? All right. All right. I'll share the tab and you tell me which are the questions where you are facing problems. I hope this tab is visible to you, right? Okay. So week 9, you had one, I think Janvi, you had a doubt, right? Tell me which question is it? What is that row value, what you are saying? Okay, all right. So here you see, did you go through the solution? Did you check it? Okay, fine. So here you see, you have to compare it with the PDF of a, what do I say, bivariate normal distribution. Okay, so here this has to be your x minus mu1 mu x by sigma x whole square. This quantity. This quantity is supposed to be your mu y minus sigma minus sorry y minus mu y by sigma y whole square. This should be your row containing quantity. All right. So then you have to sort of make equations and then uh, find out what should be the values of x and y. So since it is mean of x and y, like this is sort of a shortcut, okay? So Do you remember the what do I say? The PDF of a bivariate normal distribution? Can you tell me what it is? Hmm. Oh, okay, fine. It's okay. Wait, I'll just. Can you see my PowerPoint screen or no? The PPT is visible to you? I'm writing something. Can you see? Oh, okay, fine. I think I have to share my entire screen. It is only possible. Okay. So here, bivariate normal distribution, it looks like how? F of oh, this is actually so just give me some. So bivariate normal x1 x2, this looks like 1 by 2 pi sigma x sigma y root over 1 minus rho square. Then you have e to the power minus 1 by 2 1 minus rho square. Then you have x minus mu by sigma x whole square plus y minus mu y by sigma y whole square minus 2 rho x minus mu x y minus mu y by sigma x sigma y. This is the form of your bivariate normal distribution. Okay, so from here, wait 1 second. Yeah, you can. So here you see mu x is 3, mu y is 5. All right, sigma x looks like 5, sigma y looks like 4. Now the only thing that you have to check is that this row containing term, it should also match. Okay, so from here if I have sigma x equal to what am I saying, 5, sigma y is 4, and mu x is actually 3, and mu y is actually 5. Okay, so then 2 rho by sigma x sigma y, this should be equal to minus 3 by sorry 3 by 50. If I write it like this in this manner, or I would rather suggest 1 by 2 1 minus rho square into this thing should be equal to 25 by 32. No, let that be. We don't need that because it's totally taken as common. So this one should be equal to whatever we have, 3 by 50. So then this is 5 into 4, 20. So 1 by 10. So rho is actually 3 by 5. From here we get rho to be 3 by 5. And then we have to see if this is holding true or not. So 1 by 2, 1 minus rho square is actually how much? 1 by 2, 1 minus 9 by 25. So this is 25 by 2 into 25 minus 9 is how much? This is 14. So it will be 25 by 28. Sorry, 25 minus 9 is 16. So this is 25 by 32. Do you get it? And if you here also if you do it, 2 into 5 into 4, this is 20 into root over, so 20 into root over 1 minus 9 by 25. So this will be 20 into 4 by 5. That is also, sorry, 4. So this will be, so 2 into 20 here you have, this is 20, 2 into 20. So that will be 40 into 4 by 5. So you just cancel this, you're getting as 32. Is it okay? This is how you have to solve it. Wherever in the numerator, this is the form x minus mu x, y minus mu y whole square. Wherever you find this, you just assume this is mu x, this is mu y. And then this cross product term should also be there. Then what you should definitely do is verify whether from these points you are getting rho to be, if you derive rho from one of these components, if you substitute the value of rho in the other component, then the values should match. That's all you need to do. Okay? All right. Okay. You had a question, Mr. Abhishek. You said for week 12. Yeah, yeah. Week 12. Okay. Okay. Question number 3. Okay. Hmm. 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 All right. All right. I'll solve this. Hmm. So this here they are saying that the air pressure in new types of tires in 120 cars filled by machine is based on average 500 times with a standard deviation of 80 times. Okay. Decision for testing mu equal to 450 versus mu greater than 450 at 5% level of significance. So here this is one sample mu test. So H naught is mu equal to, so we'll assume that air pressure follows normal mu and 80 square. Okay, because sigma equal to 80 is given, known. Oh, no, 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 no. The air pressure in new types of tires in 120 cars filled by machines is maintained on an average 500 times with a standard deviation of 80 times. So this is not sigma square, this is sigma hat square. Sorry. Okay. So this is sigma square. Sigma square is estimated as 80 square. All right. So then mu 450 and H1 is mu greater than 450. So this is a one-sided t-test. So the test statistic is what? X bar minus mu naught by root over of sigma hat square by so that thing sigma hat by root n. This will follow a t in minus 1 distribution. This is a single-sided sample. Rejection rule is we'll reject H naught, reject reject H naught if and only if t is greater than Tn minus 1, Tn minus 1 and alpha. This is your rejection rule. Or in terms of p-value, probability t greater than t observed should be less than 0.05. Yes, this is T observed greater than this one. So Tn minus 1 that we have to find out Tn minus 1 alpha. So let me open R. Hmm. So what do we have here? Here we have Tn minus 1 alpha. N is how much? N is 120. So Tn minus 1 alpha, this T is also a symmetric distribution. So it should be that point above which 0.05 area lies. So we have to give Qt, then we have to provide n minus 1 that is 119 and alpha is 0.05. Sorry, first we have to give 0.05, then df equal to 119 and then you have to give lower dot tail equal to false. So this point is 1.65. This point Tn minus alpha, this is actually 1.65. And what is your T observed? What is that value? That is actually 500 minus 450 by 80 by root 120. So how much do you get this to be? 500 minus 450 divided by root of 80, sorry, 80 by square root of 120. So this value is 6.84. T observed 6.84. Since this is greater than the cutoff point, that's why H naught is rejected. H naught cannot be accepted. Okay. Hmm. Yes, yes. Okay, fine. So here I'll solve question 9 also. So, so let's say this is your question, right? Here. So 12 patients were given 1 gram of medicine. Another group considered was given placebo. Okay. So this was continued for each volunteer until a doctor who did not know length of the time was recorded. And this is actually this is not a paired t-test. This is actually a two sample t-test. All right. So here with sigma A and sigma B unknown. Okay. Because we are not given what is the distribution or the variation of the A cohort or variance of the length of time for the A cohort and that for the B cohort, right? So since sigma A and sigma B is unknown, we are going to get a pooled estimator if you remember. So then the test statistic actually becomes like this. This is x bar minus y bar by root over NA minus 1 SA square plus NB minus 1 SB square by Na plus Nb minus 2. Okay. And this under H naught will follow Na plus Nb minus 2. Now what is your H1? Conducting to test if the medicine is more effective. Medicine is more effective means if mu A minus mu B. Mu A is treatment. Okay. Treatment time. Yes, this is with respect to treatment time. Not treatment time, this is length of disease. So length you would want to reduce. Mu A, ideally you would want to be less than mu B, right? So mu A minus mu B, H1 will be mu D is less than 0. So this will be a left tail test. Is it okay? Okay. So here you have been asked to test if the, oh, all right, I'll do it. So this is X. X is actually, just remember, this is your treatment group and this is your placebo. Alright. So test is X bar minus Y bar by whatever it was, Na minus 1 Sa square plus Nb minus 1 Sb square by Na plus Nb minus 2. This follows Tna plus Nb minus 2. This much is clear. Now, X stands for treatment group and Y stands for placebo. Okay. Your metric is what? Mu X is actually what? Duration of disease for patients administered with treatment. And mu Y is the same thing but placebo administered. This is what is the metric that you are considering? Duration of disease. If you want a medicine to be effective, let's say you have fever and I suggest some paracetamol to you. Now, if your fever reduces in 2 hours with the medicine, but if I give you salt water, that fever reduces by 3 hours. Okay, so the average duration for the disease to persist after treatment, that you would want to be lower than the average duration for which the disease persists under placebo conditions. Then only you will say that my paracetamol is effective in reducing fever. Okay, so then mu x minus mu y, H1 is mu x minus mu y because everything is x minus y here. This should actually be less than 0. Do you understand? So if H1 is less than 0, then the rejection rule is we'll reject H0 versus H1 if and only if T observed is less than T N1 plus N2 minus 1, 1 minus alpha. So here this T1 minus alpha is this point. So Na is how much? Na is 12, Nb is 10. So this DF is actually 21. So if I have to get it, I'll do QT 0.05, DF equal to 21 and lower dot tail equal to true because I want the below area. So this point is actually minus 1.72. Alright. And then if you calculate T observed, how much do you get your T observed to be? This is this thing. T observed is how much? T observed is X bar. If you calculate, what is the treatment, average treatment with medicine? Do you remember? Okay. Okay. This is X bar. Can you do it? 16.66. Okay. So this will be 16.66. This one, placebo, 2. Okay. Mean of placebo is 17. Okay. So this is actually 16 minus 17 by, then if I have to do this, SA square. So this would be 11 into SA square plus 9 into SB square by 21. SA square I'll find out here. Wait, variance of treat 0.833, and this will be variance of placebo 0.722. 0.722. So I'll just find out how to do T observed equal to mean of treatment minus mean of placebo, okay, divided by square root of 11 into variance of treatment plus 9 into variance of placebo, okay, divided by 21, okay. So T observed is minus 0.38. This you'll find over here. See, T observed minus 0.3859. So this is minus 0.3859. And what did we find? Our cutoff that is, this point is minus 1.72. And T observed is here minus 3.84. So what do? We therefore reject the null hypothesis. Okay. Also the value is different. Oh, okay. The value is different. Okay, I see. This shouldn't be the case. One second. Okay. Hmm. Of course. Hmm. Hmm. I understand. Uh, the two lengthy questions, I don't think it'll come. Did you check the pattern, question pattern? Do you have any idea? Yes. Ah, ah. Hmm, hmm, hmm. Okay, one second. This we were solving like this. No, let us just do a T dot test on treat and placebo. Let me just find out if I made any mistake or not. Treat dot test placebo, and then alternative is what? Alternative is actually less, right? Alternative is less paired here. Less is this thing. We are doing x minus y, no? So our H1 was mu x minus mu y. Less than 0 we are testing. No, we have to do one-sided. Okay. So if we do paired equal to false and conf level equal to 0.95. We are not, nowhere is it mentioned that the variance should be same, right? This was continued. Okay, it's not mentioned that the variance should be same. So then var dot equal is actually false. So let us see. Okay, so then this they are saying T is 0.88561. Is it the same as what we calculated? No. And p-value is 0.193. It's not matching with them also. If we do it alternative, let's say two dot sided. So they are doing a two-sided test. Okay, fine. But why will they do a two-sided test? Let us look at this. If the medicine is more effective than the placebo, I think there is some problem with the because if the medicine is effective, then the length of time the disease lasts should be less, no? Yeah, I no, no. Here you see, just forget about the t value for the time being. Okay, you just try to formulate the hypothesis. If they are asking that the medicine is more effective, so if medicine is more effective, wait, let us read it. This another group was given placebo, continued until for each volunteer until a doctor who did not know decided that the volunteer was no longer suffering from the disease. Length of time disease lasted, that was recorded. So if the length of time disease lasts is greater for placebo than that is for medicine, then only the medicine should be called effective. What happens if we do this, let's say, equal variance true? Is it coming? Hmm, it's the same thing. But two-sided they are doing. This is where I have a problem. No, p-value got it's the same thing, not the t-value. Okay. Yeah, t is matching. Yeah, t is matching. That is fine. Yes, because where y dot equal should be true because we are assuming a pooled variance that would be representative of both. My bad, this will be true. An alternate if it is less, then this is minus 0.8796 and p-value is this thing. P-value is definitely incorrectly specified over here. There's no question about it. df df equal to 20. Oh, sorry. It should take df equal to 20. This is n1 plus nv minus 2. No, I made a mistake, calculation mistake over here. This is 12 plus 10 minus 2. So, yeah, that was the problem. So here, this would be actually divided by 20. Okay. And here I think I made some errors in the brackets. Something is wrong over here. Yeah, you can run your program. This will definitely be 20. Ah, brackets issue. Even I feel it's a bracket issue. No, not yet. Anyway, here I'll do 11 into variance of treatment is this thing, plus 9 into variance of placebo. This is this thing. This entire 15 divided by 22. Okay. Wait, one, this one, and then this one, and this one. This will be 0.7122. So here, if I do a square root of this thing, then what do I get? 0.84. Then mean of this minus mean of this, how much? This is this thing. So I'll do a this divided by this thing. Oh, again, I'm not getting this value. Please try it out. So definitely in that question, p-value is incorrect. Did you get the test statistic value by any chance or no? Were you provided the solution at least? Yes, but of course, p-value, how will you calculate? First, you have to get t observed. Okay, then you have to find out probability. This t with 20 df is less than t observed. This thing you have to calculate. How will you do that? You have to do pt and then you have to give t observed and df equal to 20. This is going to give you your p-value. If this is less than 0.05, then we say we reject. If it is greater than 0.05, we say it is accept. Okay, so there is some problem in this solution. The t statistic itself is not coming. I will please give me some time. I'll look into it and keep an eye on the discussion forum. I'll clarify it there. Okay, I'll see if there's any mistake from our end, any of us end, and then I'll update it to you. Yeah, I'll look into it. This is question number three, right? No, not three. This is question number nine. Okay. All right. Let me see if when see here we are doing the same thing. Where dot equal to true means a logical variable indicating whether to treat two variances as being equal. If true, then the pooled variance is used to estimate the variance. That is what we are doing. We are estimating the pooled variance. Why is it not happening? Sorry. Here again, this should be divided by 20. Same mistake I'm keeping on making. Wait 1 second. N1 minus 1 into s square plus n2 minus 1 into SB square by 20, n1 plus n2 minus 2. This is this value. Square root of this value is 0.885. Mean minus this is 0.883. So this will be this divided by 0.885. But then also it's not coming. Hmm. Okay, this is the test for variance. This one you have to do var dot test. Same values? No, different. Here also you are facing the same issue. This is testing for variance. This you have to use sigma square. The test statistic will be different. This is not a test for mean. Question number 15. This is sigma a square equal to sigma b square versus sigma a square greater than sigma b square. This is equality of variance test. So for equality of variance, what was your test statistic? Do you remember? Okay, it must be somewhere here. Wait. Two sampled test. Hmm. This one. Difference of variances. This will be your test statistic. Okay, 1 by n minus 1, xi minus x bar square, 1 by n minus 1, yi minus y bar square. So essentially it will be variance of x by variance of y. And that you have to compare with respect to the f statistic. Okay, so here, let me go here. So you, oh, okay, all right. Okay, I'll see if I can complete this. No, no, I can spare 10 minutes. I'll try to solve it. Just give me these. I just have to input this. So I have to do it quickly. I'll do it quickly. Wait. No, 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 no. Wait. I'll do it. All right. We have the values. Fine. So x and y we have. What we have to find out is, so m is actually length of x. length array 12. Okay, and n equal to, okay, all right. So it's 10. So here what do I have to do? So this one, if you see the lecture, this is actually variance of x, and down you have variance of y. So variance of x is how much? 0.59. Variance of y is how much? 0.20. So ratio is how much? 2.85. This you have to compare with the QF. The alternative hypothesis is sigma a square minus sigma b square greater than 0. So this would be sigma a square minus sigma b square greater than 0. And for that, the test statistic is how much? The test statistic is, so greater than, this is that acceptance region, critical region. Okay, you have to give QF 0.05. M is how much? 12. M, what is the value that you have to get it here? So F1, is it not function? Okay, okay. M is how much? M equal to 12, N equal to 10, and lower dot tail equal to false. Why? QF. This is the distribution function, right? Oh, sorry. Unused argument when equal to 12. Why? F distribution Q in df1 and df2, sorry. df1 and this will be df2. This is 2.91. Oh, yes, 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 yes. That we have to do. M minus 1. Yes, yes, we have to do. Sorry, sorry. This is M minus 1. This is N minus 1 because that is the cutoff, right? M minus 1, N minus 1. So that we have to do. So this is 3.10 in that case. So here the cutoff is 3.10, and SA square by SB square is how much? We got it. That was this thing, 2.85. So since this is less than the cutoff, that's why we do not reject and accept. Is it matching? So F was 2.85, okay, and P value. Okay, then now we have to go to P value. So this is a right tail test. Okay, but I'm just telling you if there is any trouble. Since this is so the rule is what? The rule is reject H naught if and only if SA square by SB square is greater than the cutoff, right? So this is the right tail test. All right. So then your P value is probability, your F M minus 1 N minus 1 is greater than your F observed. So this is actually your PT, whatever that value 0 point, this thing that came, 2.85 lower dot tail equal to false. So that is your P value. So if I write it here, PT this thing. Sorry, not PT, PF. Extremely sorry. This will not be T. This is F. PF, this thing, and M minus 1 is DF1 is 11, DF2 is 9, and lower dot tail equal to true. So this is your 0.93, which is greater than 0.05. Therefore, do not reject. Sorry, here I wrote incorrectly. So this is less than, so this is do not reject. P-value is not matching. Yeah, that's why it will not match. It's given in that way. P-value is mm, oh, sorry. I'm saying this and I'm putting it in a different way. This is probability greater than F observed, right? So the lower dot tail should be false. I have written true over here. This is 0.063. It's option B. Is it okay? All right. All right. You're most welcome. Okay. Okay. So now you're confident, right? Once you have the rule, based on this equation and rejection, you have to formulate your p-value. If you have questions and doubts, you can, this lecture I'll upload maybe by tomorrow. You can look at how it is devised. If you have queries, you can send a text on the discussion forum. We'll address it. Thank you so much for joining. I wish all you guys all the best for your exams. Do well. Thank you, thank you. Thank you. It's very good to hear. Thank you so much and all the best for your exams. If not anything else, then I'm going to close today's session. I hope you have a good day. Thank you. Thank you.